Swayam Prabha. Digital India. Educated India.
Welcome back to the video course on fluid mechanics. In the last lecture, we are discussing about the pipe flow systems. We have seen the pipes in parallel, pipes in series. Like that, we can have other systems like branched piping systems and pipe network systems. So, we have seen that most of the time we will be solving this pipe flow systems either in parallel, series or branch types of system. We will be solving mainly by using the energy equations between various sections, and then we will be utilizing the continuity equations to get a system of equations, and then we will be solving for the unknowns, whether it can be the unknowns can be the discharge at various locations, or it can be the at various pipes, or it can be the head particular locations. So, we will be solving the fundamental, we will be writing all the equations for the by using the energy equations, and then also the continuity equation, and then we will be trying to solve the systems. So, in the last lecture we have discussed about the pipes in series system and the pipe in parallel system. So, now today we will discuss the branched pipe systems or branching of pipe system. So, here the branching network is made up of either 3 or more elements connected to a single junction. So, here say a number of say maybe we may be connecting a number of reservoirs or number of tanks, and then number of piping systems will be there in between them. So, there is as such there is no looping or say there is no networking of the pipes, but we are connecting simply connecting various reservoirs or various tanks together to form the branching pipe system. So, here there is no closed loop exists as such. So, say for example, if you consider a system like this, so here we have 3 reservoirs, reservoir A, reservoir C and reservoir D, and we connect these 3 using 3 pipelines. So, here pipe 1, pipe 2 and pipe 3. So, there will be a junction at B. So, we will first discuss how we can solve such a pipe kind of problem where branching of pipes takes place. So, here the known values may be say the head values at our elevations or head at reservoirs A, C and D, and unknowns may be the discharge through each pipe 1, 2, 3, and then what is the head at location B. So, first we will discuss how we can solve such a kind of a typical kind of this kinds of branching pipe system, and then we will discuss about the pipe network. So, now as we discussed earlier, so here also we will be using the basic energy equation between say between 2 reservoirs or between 2 points, and then also we will be using the continuity equation say wherever the junction comes. So, as we discussed earlier. So, this kinds of problem, the analysis direction of flow we do not know. So, you can see that depending upon the elevation here A, C and D, the flow can be this direction like as shown in this arrow mark, or depending upon the elevation of D and C, it can be the other way also. So, we do not know what is the direction of flow. So, we will assume the direction of flow and then we will work it out and see whatever we assumed is right or not. And then as I mentioned earlier, the energy equation for each element is written using an equivalent length to account for the minor losses. So, as we discussed in the case of pipes in series and pipe in parallel system. So, for branching pipes, say for example, if you consider we will consider now this between section A and B, then B and D and B and C. So, if you consider section between A and B, we can write the energy equation for each pipe element like as given here. So, between A and B, P by gamma plus Z at A minus P by gamma plus Z at B is equal to R1 bar Q1 square, where Z is the datum elevation at corresponding location, say corresponding to A and B, and then where R1 bar is the equivalent resistance coefficient, as we discussed in the earlier lecture when we discussed about the pipe in parallel system or pipe in series system. So, similar way now equation 1 is written for between the energy equation between A and B. So, now if you write the energy equation between this B and C, here we can write P by gamma plus Z at B minus P by gamma plus Z at C is equal to R2 bar Q2 square, and similarly we can write between B and D, between this point B and D as P by gamma plus Z at B minus P by gamma plus Z at D, that is equal to R3 bar Q3 square. So, where this Q1 is the discharge through pipe 1, Q2 is the discharge through pipe 2 and Q3 is the discharge through pipe 3. So, now these are the energy equations which we have written between A and B and B and C and B and D. So, now next say the piezometric heads at location A, C and D are considered to be known, as I mentioned. So, the reservoirs which are open or which we consider that head is known, we assume that this head, the piezometric heads at A, C and D are known. Then the unknowns are the piezometric head at B and the discharges Q1, Q2 and Q3. So, by considering this typical problem, so here this we assume that here the head value, the piezometric head is known at A, D and C, and but the discharges Q1, Q2, Q3 are not known, and also the head at B. So, there are 4 unknowns. So, this Q1, Q2, Q3 and the head at B. So, here at junction B is concerned, here we can assume that if we assume that the flow is taking place this direction, Q1 to the junction and Q2 from the junction and Q3 from the junction. So, that we can write the continuity equation with respect to this Q1 minus Q2 minus Q3 equal to 0 as in equation number 4. But if we assume the other way, Q1 this direction, Q2 this direction, Q3 towards the junction, then we will be writing Q1 minus Q2 plus Q3 is equal to 0. So, we can assume the direction initially, and then we will do the calculations, we will find out the discharge, and then accordingly we can later we can adjust the direction depending upon the our assumption. So, now here we have 3 energy equation as written 1, 2, 3 here between B and C and between B and D, and then either one of these we are having one continuity equation either 4 or 5. So, let us use this equation here by assuming that Q1 is flowing this direction, Q2 from the junction and Q3 also from the junction, Q1 towards the junction. So, we use this equation number 4. So, we have 4 equations and 4 unknowns. So, that we can easily solve the system. So, the unknowns here are Q1, Q2, Q3 and the head at junction B, and then the equations are at junction B we have written the continuity equation, one equation, and then we have written 3 equations with respect to the energy equation between A and B, B and C and B and D. So, these 4 equations we can solve to find out this 4 unknowns. So, here in this slide the basic steps for such kind of solutions are given here. So, what we assume here, we start with step number 1, assume a discharge of Q1 in element 1 with or without a pump. If there is a pump also in this particular system, we have to consider that pump separately. So, we assume a discharge Q1 in element 1, then establish the piezometric head H at the junction by solving equation number 1, and then we compute the discharge in the remaining using equations 2 and 3, and then we substitute Q1 in equation 4 to check for the continuity balance. So, flow imbalance will be delta Q is equal to Q1 minus Q2 minus Q3. So, basically we assume that say we start with some assumption of the flow through one of the pipe, and then accordingly then we solve equation 1 and equation 2 and 3, which are the energy equations, and then we put back the continuity equation and see that whether there is an imbalance is there, and then if there is imbalance we will again iterate. So, it is an iterative procedure, the solution is iterative. So, then the fourth step is we adjust the flow in element 1 and repeat the steps 2 and 3 until delta Q is within the desired limits. So, for delta Q, so when we do the iterative procedure, we can set the prior value, this will be 0.005 or 0.0005, like that we can put some value, and then when the computer do the iteration, when it reaches this particular limit, iteration is stopped and we finally get the value. So, that is the iterative procedure generally we adopt for this kinds of problem. So, if a pump exists equation, say for example, if there is a pump say with respect to A and B, then we have to consider that pump also. So, that can be, the equation can be written as P by gamma plus Z at A minus P by gamma plus Z at B plus H P is equal to R1 bar Q1 square. So, the equation 1 is modified by adding the pump head H P. So, where H P is the pump head, and then additional necessary relationship is the head discharge curve for the pump. So, the pump which we are using, the manufacturer would have given a pump a head discharge equation for the pump. So, that discharge equation or curve we can utilize to get a solution here. So, if a pump exists in, say for example, between pipe A and B, we will be writing P by gamma plus Z at A minus P by gamma plus Z at B plus H P is equal to R1 bar Q1 square, where Q1 is the discharge through the pipe, and R1 bar is the resistance coefficient, and HP is the pump head. So, now we have seen with respect to a branching pipe system, a typical system with 3 reservoirs, we have seen with 3 pipes and then there is a junction. So, what we generally do, we write the energy equations between various points, and then also we use the continuity balance equation at junction, and then we solve for the unknown, and we have seen an iterative procedure. So, here we use an iterative procedure to solve for the unknowns, and we keep a tolerance limit, so that when the iteration reaches that tolerance, we stop the iteration and then we get the solution. So, here now we will discuss an example. So, here the example problem is for the figure given below. Say here 3 reservoirs are there. So, here at A the elevation is 10 meter, that means the corresponding to piezometric head is given as 10 meter, and here elevation is 30 meter, and here elevation is 18 meter, and these 3 reservoirs are connected by using 3 pipes, and there is a junction at B. So, here pipe 1 is between B and A, and pipe 2 is between B and D, and pipe 3 is between B and C. So, now the given pipe data regarding the pipes are: for pipe 1 the length is 1000 meter, and the diameter is 0.12 meter, and friction factor is given as 0.025, and then the minor loss coefficient sigma k is given as 5, and similarly for pipe 2 the length of the pipe is given as 1500 meter between D and B, and then also the diameter of the pipe is given as 0.16 meter, and the friction factor F is given as 0.024, and sigma k is given as 2.25 between B and D. And similarly for pipe 3 the length is given as between B and C, the length is given as 2000 meter, and the diameter of the pipe is 14 centimeter or 0.14 meter, and friction factor is 0.02, and sigma k, the minor loss coefficient, is given as 8. So, for this system we have to determine the flow rates Qi, we have to determine the flow through each pipe, and piezometric head at H at the junction. So, for this junction we want to find out Q1, Q2, Q3, and we want to find out the head at or piezometric head at H, this location we want to find out the piezometric head. So, the elevations at A, C and D are given. And also various pipe factors or pipe elements or details are given like length, diameter, friction factor and sigma k. So, we have to find out Q1, Q2, Q3 and the head, the piezometric head at H. Also assume the constant friction factors for the given pipe. So, when we consider each pipe, the constant friction factor can be considered. So, now to solve such a system, so we have already discussed a very similar system. So, now the various numerical values are given for such a system. So, to solve such a system, we will be writing the equation, energy equation and the continuity equation as we discussed. So, before that, corresponding to the minor losses, we will be finding the equivalent lengths. So, the equivalent lengths, as we discussed in the last lecture, we can see that the equivalent length corresponding to the minor losses can be written as this sigma k into d by f. So, that is the equation corresponding to the equivalent length d into sigma k by f. So, say for pipe number 1, the diameter is 0.12 and k sigma k is 5 and friction factor is 0.025. So, we will get the equivalent length at 24 meter, and for pipe 2 corresponding diameter is 0.16 and then sigma k is 2.25 and then the friction factor is 0.024. So, we get the equivalent length 15 meters. So, similarly for pipe 3 the equivalent length will be 0.14 into 8 divided by 0.02. So, that will give 56 meter. So, initially we found all the equivalent lengths corresponding to the minor losses. So, now the resistance coefficient. So, we have already seen the basic equations earlier. So, now we will be finding the resistance coefficient for pipe 1, pipe 2 and pipe 3. So, the resistance coefficient, as we discussed earlier, we can write the resistance coefficient equation as R1 bar is equal to 8 into, so F 8 into F into the length divided by G into pi square into d to the power 5. So, this equation R1 bar will be 8 into, so for pipe 1 F is 0.025 and the equivalent length is now 1000 plus 24. So, 1024 divided by G is 9.81 into pi square into D is 0.12. So, d to the power 5, 0.12 to the power 5. So, we get the resistance coefficient for pipe 1 as 8.5 into 10 to the power 4. So, similarly, we can find out resistance coefficient for pipe 2 R2 bar, that will be equal to 2.86 into 10 to the power 4 and R3 bar will be 6.32 into 10 to the power 4. So, now we found R1 bar, R2 bar, R3 bar, the resistance coefficient, and now the energy equation we can write for each pipe and we can solve for the unknown discharge. So, as we have seen earlier, so with respect to the resistance coefficient and then the energy, from the energy equation we can write Q1 is equal to say for this first pipe H minus 10 divided by R1 bar to the power 1 by 2 and then Q2 is equal to 30 minus H divided by R2 bar to the power 1 by 2 and Q3 is equal to H minus 18 divided by R3 bar to the power 1 by 2. So, here in this problem we assume that the flow direction is this Q1 this towards A and Q2 towards B and Q3 B to C this direction. So, we assume this direction and then based upon this equation. So, here the basic equations we have already seen this equation, we can now write the final equation with respect to the discharge. So, Q1 we get as H minus 10 divided by R1 bar to the power 1 by 2 or square root of H minus 10 by R1 bar and Q2 is equal to square root of 30 minus H by R2 bar and Q3 is equal to square root of H minus 18 by R3 bar. So, now as per the flow direction shown in figure, so we can write the flow direction is shown here. So, one is here, this is towards the junction and other two are from the junction. So, towards the junction it is positive and away from the junction it is negative. So, minus Q1 plus Q2 minus Q3 is equal to 0. So, this is the continuity equation. So, we can now eliminate Q1, Q2, Q3 from the above relation. So, here we have relationship for Q1, Q2, Q3. So, we can eliminate Q1, Q2, Q3 and we can write in terms of H as follows. So, here we get a function in terms of H. So, WH is equal to minus H minus 10 divided by 8.5 into 10 to the power 4 to the power 1 by 2 plus 30 minus H divided by 2.86 into 10 to the power 4 to the power 1 by 2 minus H minus 18 divided by 6.32 into 10 to the power 4 to the power 1 by 2. So, that is equal to 0 by using the continuity equation. So, now here as we discussed, we will be using an iterative procedure. So, to do the iteration, we will assume a range of values between. So, now here we got an expression for H. So, to get H, we will assume certain value, an upper limit and lower limit, and then we will write a recurrence formula, and then we will check whether we reach the tolerance limit which we set. So, here the recurrence formula. So, if you want to find out the head between an upper limit and lower limit, the recurrence formula is HR is equal to HL into W HU, W a function of HU minus HU WHL, it is a function of HL divided by W HU minus WHL, where HL is the lower limit we assume and HU is the upper limit we assume, and then WHU is corresponding the upper limit we put here in this equation. So, that we will be getting a residual. So, that will be WHU. Similarly, WHL, when we put the lower limit we get a residual, that will be the WHL, and then we find the difference, and then in that iteration we find out the head value HR. So, for this typical problem, you can see that here the maximum elevation is 30 meter and minimum elevation is 10 meter, and here the other one is 18 meter. So, we will assume a value between 18 meter and 30 meter. So, we will put an initial guess of head value between 18 and 30, and we will then do the iteration. So, the iterative procedure is given in this table. So, here we set a convergence limit of 0.005. So, here we are assumed that the H value is between 18 and 30. So, we start the iteration with a value of H as 22 meter, and then we will use the recurrence formula given here. So, in this table you can see the first column is iteration number 1, 2, 3, and here the upper value which we use head value HU and HL lower head value, and then WHU, this assumed for the corresponding upper value, the W function which is given by this equation, and then WHL corresponding to lower value and the function, and then we get the corresponding HR from this equation. Using this equation we get HR, and then corresponding that WHR, again we will find what is the residue we get here corresponding to this equation, and then we will see that what is the sign of this WHL in WHR, and then in this column here this direction, and then we will see the residue epsilon is the modulus of HR new minus HR old divided by HR old. So, we start with a value of 22 and lower limit is always set as 18. So, now after substituting 22 here, we will get this WHU as minus 0.00311, and correspondingly by putting HL as 18 we get WHL as 0.01078, and then correspondingly by solving this equation we will get HR as 21.1 and WHR will be minus 0.00079, and then since WHL is positive and HR is negative, so we will get this as negative, and then say corresponding to iteration number 1, and then the epsilon, anyway here we are not calculating since the first iteration, and then in the second iteration we will use now this HR 21.1 as our upper limit, and lower limit is already assumed 18, and then again we find out WHU. So, that will be obtained the same value minus 0.00079, and then WHL is concerned it will be same 0.01078 since the lower limit is same, and then if you calculate again HR back we will get HR as 20.89, and then the corresponding residue will be minus 0.000232, So, then again this sign will be minus here as shown, and then if you find out the epsilon, the error HR nu minus HR volt by HR volt, its modulus, we will get 0.00995. So, now we have improved the solution to 20.89, but you can see our expected error is convergence is 0.005. So, we have to continue one more iteration. So, now the next upper value is 20.89 and then lower is same, and then we again calculate WHU, WHL. So, WH is minus 0.000233 and WHL is 0.0178, and then HR we can find out here will get us 20.83. So, then you can see that the residue will be minus 0.000072. So, you can see that now here again it is minus, sign is minus, but you can see here the epsilon, which when we calculate it is 0.0029. So, which is smaller than the convergence limit of 0.005. So, here we can stop the calculation, even though some error is there, we assume that the value is almost near to 20.83. So, after this we can, if you want further accurate value, we can continue through a number of iteration, we may get almost very nearby value. Then here say let us assume that approximately the value is equal to, even though we got here as 20.83, so we will assume it is almost equal to 20.8 meter, and then we can find out the discharge. Q1 is equal to 20.8 minus 10 divided by R1 8.5 into 10 to the power 4 to its square root, we will get 0.0113 meter cube per second, and Q2 will be 30 minus 20.8 divided by 2.86 into 10 to the power 4, so its square root we will get 0.0179 cubic meter per second. Similarly, Q3 we will get as 0.00665 meter cube per second. So, like this this branching pipe system, as we discussed, we can write the energy equation, we can use the continuity equation, and then we can solve this equations to find out the unknowns like flow through each pipe, and also we can solve for the piezometric head. Say for example, here we found the piezometric head at the junction points. So, like that we can solve different kinds of problems. So, here we assumed a simple system. So, in the complex system there can be valves, there can be pumps, like that a number of components can be there. So, the branching pipe system we can solve in a very similar way. So, next topic is analysis of pipe network. So far we have seen the pipes in series, pipes in parallel, and branching of pipes. So, that is what we have just now discussed. So, now we will discuss the pipe networks. So, you can see that most of the say water supply lines, or most of the system where the a number of pipes are used and number of uses are there, say just like in the water supply system, we will be using a pipe network for the distribution. So, a simple pipe network, like you can see here in this slide, you can see a number of pipes are connected through with respect to reservoir, or there will be number of outlets, and then you can see that through there will be number of junction points, and then with respect to junction points, various junction points, we can have also loops like this. So, a simple pipe network consists of pipe elements fitted with bends, valves, joints, and number of pipes, and then also correspondingly we can say wherever pipes are joining that junction, which is called a node. So, we will be having number of nodes like this. So, this is a one node, second node, like that number of nodes will be there, and then we can also have a loop. So, like this is a typical loop. So, like that another loop. So, we can have number of loops also like this. So, a typical, this figure shows a typical pipe network. The arrows show the flow direction. So, here most of the time we can see that we may not be knowing the flow direction. Also, the flow direction may change with respect to time, also depending upon the pressure, depending upon the water going from each junction. Even the direction can also change. So, that is why we call it as a network. So, pipe networks. So, as I mentioned, the pipe network say can be typically in the case of a city water distribution system. So, where a number of say systems, number of pipes are included, a number of connections are there, number of junctions are there. So, there as we have seen, there can be multiple inlets, multiple outlets, and as I mentioned, the direction of flow is not obvious, and then direction may vary from time to time, and then pipe network, say here as I mentioned, there can be, say wherever the junctions are there, these are called nodes, and then also there are loops between that. So, here for this simple pipe network system, this is one loop and this is another loop. So, there will be loops. So, generally say we will be say considering the nodes and loops, and so we will write equations with respect to nodes and loops, and we can just compare these kinds of pipe flow systems or pipe network system with respect to electrical networks. So, you can see that electrical system is considered. So, there will be number of say system, number of wires will be connected together to form a network, electrical network. So, this pipe flow system is also we can consider say typical, say very similar to electrical network. So, this as we have seen, the major challenges here are we do not know exactly the direction of flow, and even from time to time the direction may change, and also since there are number of pipes are there, number of fittings will be there. So, all these losses we have to consider, and then also we have to see the continuity equation and the energy equation is satisfied at all nodes, and with respect to the we have to consider these equations with respect to loops also. So, these are some of the major challenges when we solve such kind of pipe networks. So, to make it simple, while solving these kinds of pipe network problems, we put certain assumptions. So, here the important assumptions are listed here. So, the assumptions here are, first one is the effect of minor loss elements generally, as we have done earlier, are lumped together with the major head losses depending upon the system. So, that is assumption number 1, and assumption number 2, the actual withdrawal points they distributed along the links. So, here you can see along the links from one to another, the actual withdrawal points are considered, and then the rate of withdrawal at a node does not exceed the rate of demand. So, each node is considered, there will be certain demand. So, with respect to that demand only, the rate of withdrawal what we consider. And then the fourth one is the velocity heads generally neglect, say since the system is so complex that if you consider all the things, it will be very difficult to solve. So, velocity heads are neglected, and a piezometric head is generally considered in analysis. So, as we have seen in the system earlier, we will be considering the piezometric head instead of the say velocity head is neglected and the piezometric head is considered. And the effect of transient behavior not generally considered in this kinds of analysis, since the analysis is so complex. So, we may not consider the transient effects. So, based upon these assumptions, we try to solve these kinds of complex pipe networks. So, generally the solution methodology. So, we have already seen in the branching of piping systems also, we consider the continuity equation and we consider the energy equation. So, very similar way also here we approach the pipe networks. So, the solution methodology includes continuity equation will be written for each node or junction. So, we have seen that say for such a system there can be a number of junctions, 1, 2, 3 like that, a number of junctions. So, first we will consider the continuity equation for each node or junction, and then net pressure difference say completely around a loop must be 0. So, here we can see that a number of loops here like this, a number of loops will be there. So, we consider the net pressure difference completely around a loop must be 0, and then third point is the head loss and pipe flow equation we use, as we have seen earlier. We will be using the head loss equation and the pipe flow equation based upon the energy equations or the Darcy's back equation we will be using, and then the minor losses are included as equivalent lengths in each pipe. So, as we assumed the minor losses we include as in the with the major losses. and then we obtain the flow through the entire network. So, depending upon the problem, there will be number of networks, so number of loops and number of junctions. So, we obtain the flow through the entire network, and then the direction of flow and friction factors. Some of the major challenges include we may not be knowing the flow direction, and also if the friction factors are not, then it will be more difficult. So, to solve these kinds of problems, we go for trial and error solutions. So, say the system is so complex, so we may assume the direction of flow, and we may start with some of the, by writing the basic equations we start, and then we assume the flow directions, or we assume some of the flow values, and then we go for a trial and error solutions. So, generally to solve these kinds of pipe network problems, we go for successive approximations. So, one of the commonly used successive approximation is Hardy-Cross method, which we will be discussing in detail later. So, now we have seen what are the major challenges to solve this pipe network, complex pipe networks, and then we have also seen the assumptions which we use to solve the system. We have also seen the solution methodology, starting from the basic equations like energy equation and the continuity equation. We try to solve the system. So, now we will consider a typical system, and then we will write the equations which we can utilize to solve such a system. So, now here in this slide we consider a pipe network system. Here it includes two reservoirs at A and F, and then we have 7 pipes connected like this, and we have here 4 junctions, here E, C, D and B, and the reservoirs are located at A and F, and there is a pump at this location P. So, here we have 7 pipe elements. So, the above network consists of 7 pipes, 2 reservoirs and 1 pump, and then we have 4 junctions or 4 nodes. So, we will now see how to write the system of equation for such a system, typical system, and then for any kind of system we can just extend in a very similar way the analysis considered, and then the solution part we will discuss in detail later. So, now here between this A and F, so here we have got 2 reservoirs. So, these 2 reservoirs A and F are assumed, the values, the hydraulic gradient lines at A and F are assumed to be known. So, or the piezometric heads are known at A and F, and these nodes here at A and F are called fixed grade nodes. So, this A and F we consider the values are known, and we call them as fixed grade nodes. And then here this system is considered from C and D, there is the flow is going out. So, the discharge QC and QD, these are outflow demands, and C, D, B and E are interior nodes or junctions. So, here we have C, D, B and E. So, we have 4 interior nodes or junctions, and initially, as we discussed, initially flow directions are not known. So, we can assume the flow directions. Say for example, this system is considered, we can assume that the flow is going this direction, A to B this direction, and B to D this direction, B to C, and then C to D flowing, and E to D flowing, but C to E and F to E, these are the flow directions, and here outflow from D and C. So, now we assume the flow directions. Now, between for each junction or each nodes, we can write the energy balance equations for each pipes we can write. So, if we consider A and B, so that means this point A to B. So, between A to B we can write HA minus HB plus HP Q1 is equal to R1 bar Q1 square. So, that is the energy balance equation between A and B. So, similar way between B and D. So, B to D. So, this is from B to D we can write HB minus SD is equal to R2 bar Q2 square, and similarly between C and D HC minus SD is equal to R3 bar Q3 square, and between B and C it is HB minus SC is equal to R4 bar Q4 square, and between C and E HC minus HE is equal to R5 bar Q phi square, and between E and D, H minus SD is equal to R6 bar Q6 square, and HF minus between F and E, it is HF minus HE is equal to R7 bar Q7 square. So, these are the equations with respect to the energy balance, and now we have 4 junctions or 4 nodes. So, we can write the continuity balance for each interior node. So, here we have 4 junctions. So, for each junction or each node we write the continuity as Q1 minus Q2 minus Q4 is equal to 0. This is coming with respect to, we are assumed the flow direction with respect to the assumed flow direction, we are writing the continuity balance for each interior node. So, Q1 minus Q2 minus Q4 is equal to 0, and then Q2 plus Q3 plus Q6 is equal to QD, since there is an outflow at D, that is equal to QD, and Q4 minus Q3 minus Q5 is equal to QC, and since there is an outflow at C, and then Q5 minus Q6 plus Q7 is equal to 0. So, these are with respect to each node. We have written 4 equations like this. And then as far as pump is considered, so here we have got a pump at this location. So, for pump we can write an equation like this: HP Q1 is equal to A0 plus A1 Q1 plus A2 Q1 square, where A0, A1 and A2 are non-coefficients. So, this equation corresponds to the pump curve. So, now all the equations are written here with respect to the energy balance equations and the continuity balance and the pump equation. So, here we can see that, say, the unknowns generally, say here this system is considered, the unknowns are the discharge through each pipe. So, we have got 7 pipes. So, Q1 to Q7, Q1, Q2, Q3, Q4, Q5, Q6, Q7. So, 7 unknowns, and then the unknowns will be the heads at each interior node. So, HB, HC, HD and HE, and then corresponding to the pump, since the discharge is not known. So, HP will be another unknown. So, we have got here same 12 equations. So, here we can see, here we have 7 equations, and here also we have 4 equations, and then we have 1 equation corresponding to this pump curve. So, we have 12 equations, 7 energy equations, 4 continuity equations and 1 pump equation, and we have 12 unknowns. So, this way the solution is okay, since we can easily get a solution, 12 equations and 12 unknowns. So, now since you can see that these equations are combined with respect to the discharge and heads. So, these equations we will be trying to reduce in number by combining the energy equations along special paths. So, here we can see that we can have different paths can be written like this or like this. So, along different paths we will combine the energy equations such that we can reduce the number of equations and correspondingly the number of unknowns also. So, we will assume let the drop in hydraulic gradient line for any pipeline, that is I be designated as Wi. So, that as we have seen, this drop in hydraulic gradient line can be Wi is equal to Ri bar Qi square. So, this is a relationship we have seen earlier. So, this is the drop in HGL for any pipe element I is Wi is equal to Ri bar Qi square as in equation number 4. So, now for the system you can see that we have two with the possibility, there are possibility of 2 loops, one is this loop and another one is this loop. So, there are possibility of 2 loops here for this typical system. So, 2 closed paths or interior loops are identified, and flow is considered positive in a clockwise sense around each loop. So, here we consider the flow is to be positive clockwise, and then the anti-clockwise we consider as negative. So, now we can write the energy balance, we can write around loops 1 and 2. So, if you consider here this figure, you can see that say this loop is considered, this loop, say this flow is going, this is same direction and this is the opposite direction. So, this is clockwise, this is anti-clockwise, and this is this way clockwise, and this is the anti-clockwise. So, correspondingly between these 2 loops we can write W6 minus W3 plus W5 is equal to 0, and second equation is W3 minus W2 plus W4 is equal to 0 as in given here. So, now with respect to the energy balance with respect to loops we got 2 equations. So, now energy balance from A to F. So, if we consider here this figure, say from this reservoir A to reservoir F. If we consider here, we can write the equation from A to F by considering A, B, D, E, F. This A, B, D, E, F, here A, B, D, E, F. So, if we consider this, we can write H A plus the head at A, H A plus H P the pump head minus W 1 minus W 2 plus W 6 plus W 7, that is equal to H F. So, we can write the energy balance between A to F in the direction of A, B, D, E and F, like in equation number 6. So, now the path energy equation 6 connects two fixed grade nodes. So, depending upon the network, we can see where are the fixed nodes. So, between these fixed grade nodes, we can write the path energy equation as written in here, in this case equation number 6. So, such a path is termed as pseudo loop. So, here this is called a pseudo loop because an imaginary pipe with infinite resistance or no flow can be considered to connect the two reservoirs. So, that is why it is called a pseudo loop. So, for the pseudo loop which we consider here, this equation is written, and now we will substitute the pump equation and the friction equation into the energy equation above this equation. We will get, we will write all the corresponding equations here, and then this equation, equation number 5, we will get minus R3 bar Q3 square plus R5 bar Q5 square plus R6 bar Q6 square is equal to 0, and second equation will be R2 bar Q2 square plus R3 bar Q3 square plus R4 bar Q4 square is equal to 0. So, then if you write corresponding to equation number 6, when we substitute all the values, it will be correspondingly for the pseudo loop, it will be minus R1 bar Q1 square plus corresponding to pump equation S0 plus A1 Q1 plus A2 Q1 square minus R2 bar Q2 square plus R6 bar Q6 square plus R7 bar Q7 square plus HA minus HF is equal to 0. So, similarly, with respect to this, we have already seen this equation here, the continuity balance. So, that also we can write here Q1 minus Q2 minus Q4 is equal to 0, and then Q2 plus Q3 plus Q6 is equal to QD, and Q4 minus Q3 minus Q5 minus QC, Q5 is equal to QC, and Q5 minus Q6 plus Q7 is equal to 0. So, now we have written all the equations with respect to the discharges, since here in these equations HA and HF are already known values. So, now we have 7 unknowns Q1 to Q7, all the discharge values, and here we have now this 2 equations and this third equation 3 plus this 4 equations. So, we have 7 equations and 7 unknowns in terms of the discharges Q1 to Q7. So, here now we can solve the 7 equations first to find out the discharges Q1 to Q7, and then we can solve for the head values. But here you can see that the equations, like here the energy equations, you can see these equations are non-linear. So, we have to either linearize this equation or we have to go for an iterative solution. So, now that is the generalizing for this typical network which we have considered. We have seen how to write the equations, how to see the various equations for with respect to continuity or with respect to the energy, and then with respect to pump equation we have seen the various system of equations. So, this we consider for a typical system like this. This is the typical system which we consider. So, now based upon this the equations which we have written, we want to generalize. So, for a general system, what will be the equations? So, here for a generalized network, the equations can be written. So, first one is the continuity equation. At jth interior node, we can write sigma plus or minus j qj minus qe is equal to 0, as in this equation number 8, where j refers the pipe connected to particular node, say which node we connect. So, that is for this j, and QE is the external demand. So, if there is any flow going out from the particular node, that is called external demand, and then positive sign for flow into the junction. So, we have seen various junctions. So, whenever a flow is going to the junction, we consider it as positive, and when the flow is go out of the junction, we consider the flow it is as negative. So, in this equation number 8, we have sigma plus or minus j qj minus qe, where q is the external demand and qj is corresponding to that particular pipe J, and negative is for flow out of the junction and positive is flow into the junction. And then the next equation, generalized equation, is energy balance around an interior loop. So, we have seen as in the earlier case there were 2 loops. So, depending upon the problem, number of loops may be there. So, for each loop we can write the equation. So, the energy balance around an interior loop we can write as sigma plus or minus I W I is equal to 0 as in equation number 9. So, here we consider positive as clockwise and we consider negative as anti-clockwise. So, here I pertains to the pipe that make up the loop. So, this is the second equation, the generalized equation, and first one is continuity equation and second one is the energy balance around an interior loop. Now, next lecture we will be discussing how to solve this kinds of system and then to get a solution, whether we go for linearization or we go for iterative method. So, we will be discussing in detail about the solution techniques in the next lecture for the pipe networks.